everybody. So as you know, the black holes are the most one of the most energetic objects in the universe. They produce enormous amount of radiation and also mechanical energy as jets. So when we say observing black hole means observing the radiation which is coming from the accretion disk or from the jet or from the surrounding medium. So for that, black hole needs to accrete. That means someone is supplying matter, and that is the companion which can be identified from the optical observation. But so far, only 20% of the black hole candidates are dynamically confirmed from optical observation. Therefore, there are lots of scope to put some prediction about this binary system, so that in future we can confirm them using optical observation with high resolution telescopes. So here I'll talk about estimating binary parameters for this particular black hole transient, which was observed by Astrosat in 2018. So from this diagram you can see that there is one hotspot at the outer edge of the disk. So matter is accumulating at that radius. When it crosses some critical accretion rate, convective instability grows in and turbulence starts. So viscosity goes up and matter starts transporting angular momentum, almost 90% of its angular momentum outward, so that it can fall into the black hole. So viscosity is crucial, which is actually triggered by the accretion rate. So once the matter starts falling in, we can see different energetic radiations. So at the outer radius, it has lots of angular momentum. Viscosity transports almost all its angular momentum, and as I said, this gravitational energy is released by radiation and or by some outflows. So this accretion was modeled almost 50 years ago in 1973 by Shakur and Sunai. In this classic paper, they showed that there is a thin disk, and they considered the viscosity as a parameter because the origin of viscosity, it requires a huge amount of viscosity, which can be generated due to some turbulent effect or magnetic rotational instability. So putting all these effects aside, they considered this viscosity as a parameter. So here you can see that the mass is falling in, angular momentum is transporting out. But this type of disk is optically thick, geometrically thin, so they can produce only multicolor black body like this, and that this black body spectrum cannot explain the whole outburst profile or outburst spectral states of the black hole candidates. So we need something more. So these are the typical spectral states. If you consider only one isolated black hole, you do forget about this companion, just consider an isolated black hole. You can see that when the disk is very cold, you can see that the spectrum is dominated by the black body radiation, and the power law component is negligibly small. Now, when the black hole starts accreting and disk become hot, it produces power law component, and this is simply the inverse quantized photon. So this disk is cold, it produces soft photons, low energy photons, almost less than 1 keV photons, and those photons get scattered by this inner hot region because there is their temperature is almost around 100 keV. So electrons and photons are decoupled. So these hot electrons can upscatter these cold photons, and they become hard, and we get this power law component. So in some cases, we can also observe FEK alpha line from this cold disk. Now, if we follow one outburst like thoroughly, we can see that the spectral state changes, like spectral slope changes. This is HS means hard state, and this is a soft state, and from hard to soft, it passes through intermediate states, and spectral slope changes. So this can be explained by this intermediate states using Q diagram, which you can see, like often you see here in many talks, and you can there consider hardness versus intensity diagram. So this is really under question, because this hardness ratio has no general definition. Depending on observations, depending on black holes, depending on telescopes, instruments. If you have observation, then you classify this hardness from one energy band to other energy band. If you do not have observation, you change your mind and define hardness in a different way. So this hardness ratio is not the proper representation of this type of spectral states. You need something more, something basic, more fundamental, and that is mainly the accretion rates. So if you can see two accretion rates. When disk is hot, it has a hot flow. When disk is cold, it's cold flow. So if you take the fundamental flow parameters like accretion rates, you can easily explain this type of spectral state transition. Or you can consider viscosity parameter, which actually rises during the outburst phase. That means during this phase, viscosity increases, and when the outburst declines, you get fall in viscosity parameter. So this type of curves can be explained from more fundamental ground. So in time domain, that is in spectral domain, in time domain, what we see, our telescopes, just our detectors collect some photon counts with time, but we do not see much here. If you take the Fourier transform of this, you can see that there are certain peaks. These peaks may appear like this is the fundamental one, this is the harmonic, but sometimes you can see more than two, or sometimes only the fundamental one, depending on the accretion processes and all the physical underlying physical processes that are governing this type of effects. So depending on this frequency values and this half width, full width half maximum, this Casella classified QPOs type A, B, and C. But in this talk, I will mostly talk about type C, low frequency QPOs. Yeah, whatever I am talking about is low frequency QPOs below 30 Hz. So now the question is, are they interlinked? The answer is yes. So if you move from hard to soft state through intermediate state, you can see that how the spectrum is changing and corresponding the appearance of QPO and its disappearance. So they are definitely interlinked, and one should explain from the same model both the properties. So there are models like this is a hot corona and cold disk is sitting there. As I said, this cold photons get scattered by this hot electron cloud and produce hard radiation. Once they scattered by this hot electron, every time they scatter, they extract energy, because this is inverse Compton effect. So they extract energy, and the size of this corona region shrinks. So therefore, all these effects should take into account during modeling. So there is another cartoon model, as you can see, that a corona is sitting here. In one case, sitting at the equatorial plane. In one case, it is at the vertical direction. And some atomic transition is also occurring. This type of transition can produce iron line that I showed earlier. So mainly three key components are observed or needed to explain outburst feature. Thin disk that I already mentioned 50 years ago people proposed, and this is corona. But in this model, we do not know this corona are static or dynamic. Definitely it should be dynamic, because the whole system is dynamic. Now another component is jet or outflow, which can also behave as a corona, because jet is also hot. So now, these questions are not yet clear. How does the corona form from this model? Because in this model, just corona is sitting somewhere, and they are scattering photons, producing hot radiation, and that can feed the data. But why the corona is forming, how the corona is forming, what is the shape of the corona? Is the corona dynamic or static? Can it be explained from the both spectral and QPO properties explained simultaneously from this model? The answer is no. None of them can explain. They can nicely explain spectral properties, but none of them can explain timing properties. So alternatively, recently we have proposed another model which is called jet cap model. So this is jet in two-component advective flow. As you have seen from this previous slides, there is one component at the equatorial plane which is called Keplerian disk, and the other component is hot flow. So we have two components, and the other component is the jet. So in that's why this is accretion ejection based model, and we solve hydrodynamic equations of the inflow, and also the outflow is coming from the same solution, from the same inflow parameters. So this is the model geometry. This is Keplerian disk. This is a hot flow, which is sub-Keplerian, because this flow is basically from Rosslow, but the hot, which is sub-Keplerian flow, it has low angular momentum, it moves faster. So once it moves faster, it forms this hot corona producing shock. Because when the flow is moving inward towards the black hole, its velocity increases. Once the velocity increases, it becomes supersonic. Supersonic flow can produce shocks. Once it satisfies this Rankine-Hoover shock conditions, like energy balance and pressure balance. So this produces shock, and shock generates the heat. This heat actually is puffing up the inner region and producing hot corona. So this is the boundary layer we can see of the corona, and this region upscattering one component, but it is also possible that the hard radiations which are coming out from this region may also get scattered by the jet, because jet is also hot, so it can also scatter this radiations. So we have also taken into account jet has velocity effect, so that's why it is jet bulk motion quantization. So once we do that, we come up with 6 parameters, like mass of the black hole itself is a parameter. If we do not know mass of the black hole, we can estimate from this model. And the other one is the disk accretion rate, which is cold one, and the halo accretion rate, which is the hot one, and the shock location, which is basically the size of the corona, and the shock compression ratio. Because when matter is moving, it becomes supersonic to subsonic after forming shock. So there is a velocity jump, and that velocity jump is actually compressing the flow. So compressional heating effect is also there. So that is the reason of this puffing up. So this is heating is there. Earlier I mentioned cooling is there. So when cooling and heating, it's like a tug of war. Once they have different time scales, but at some point when these two time scales match each other, resonance occurs, and we get this QPO features. So this is the spectrum which is coming out from this model. So different components have the same color here. So this is pure black body, multicolored black body. This is at the shoulder of the black body, you can see, which is basically scattering of these photons by the jet. And there is a Compton hump above 10 keV, which is because of this scattering of these photons by the jet electrons. So if we talk about how the spectral state changes in light of this model, so we can say if you keep all of the parameters and only change the accretion rates, what you can see that when the disk rate is low, halo rate is high, you get hard state. Now, as the disk is moving in, matter is like companion is keeps supplying matters. So what will happen? Disk rate will increase. So when both of them are more or less comparable, we can get a hard intermediate state. When disk rate is little bit high compared to halo rate, but more or less similar, we can get soft intermediate. And finally, when disk rate is very high compared to hot flow rate, we can get soft state. So what do we see in outbursting light curve? So once matter accumulates at the outer boundary, flare starts. So this is the flaring point, and then matter starts accreting to the central black hole. So its count rate goes down, and again when because matter accumulated starts accreted by the black hole, its value goes down, but company is supplying again, so when it reaches its critical value, it again produces flare, and again we can see this decay light curve. So this type of light curve can be explained from irradiation mechanism. Irradiation means when radiation which is coming from the central black hole can heat up the disk, and it can produce all kind of instabilities, so that matter can start accreting. So there are using this irradiation mechanism, if one solve these equations, one can get exponential profile. The first one you can see it's in viscous time scale unit. So in one viscous time scale, one can see this type of profile, and then again this is the flaring state, and this light curve decays in exponential form, and later when flux goes very low, it follows some linear profile. So these are the equations after deriving irradiation mechanism, and one can see that the decay profile is like e to the power minus t by tau, and it is also a function of R11. R11 is the outer radius of the disk in 10 to the power 11 centimeter unit. So what these two are the key factors. So what we have, this R11 we do not know, we can estimate. So here we have scope to further model this type of formalism. So what I did, I took into account this companion properties like the binary parameters like the orbital period, companion mass, and if I consider all those things, I can actually reproduce the same curve as a function of orbital period and companion mass. So I did the same, I followed the same formalism, but did some detailed calculation, including binary parameters as well as the viscosity parameter. They consider viscosity fixed like 0.2, which is typical viscosity, but viscosity can also change. Viscosity is also a function of the height of the disk or disk aspect ratio. So these are the plots that variations that I got of the mass acquisition rate. So now I move to Swift J1658 source, and this source was observed by Astrosat 3 times in 2018, in February, March, and at the beginning of March and at the end of March. So especially I'm showing this observation because all those other light curves are more or less average count rates are more or less same, but they do not show much variability. But this curve shows some extreme variability. As you can see, in few kilosecond time scale, flux goes up and then went down. So this type of behavior, and then again it goes up. So this type of behavior is called flip-flop behavior or flux alternating behavior. So this why this is like happening in a daytime scale. So that is one key question for this source, and this source also put QPO frequencies for all observations. This observation 1, 2, and observation 3 also showed QPO frequency. So what is the origin of QPO frequency? And also this source sort of high absorption actually is required to feed the spectral data. So all these questions we try to explain in using our JCAM model. So here I again showed this the most interesting one, observation 2, and we can see that this data can be fitted using this model nicely, and these are the key parameters. So this is the acquisition rate we got, which is quite high. So this high acquisition rate may indicate that this high column density might be because of the wind which is launched from the disk, because if your acquisition rate is high, it can you can get radiatively driven winds. So that can block the central radiation. So that is that can be one reason. And we always got the cold flow rate. This is cold flow rate is always higher than hot flow rate. So that means the spectral state is either soft or it is trending to soft. So that is our conclusion. So and also as mass is a parameter, we have estimated, we have fitted the data, and we got the mass around 14.1 solar mass. So we can also infer the mass of the black hole. So using all these parameters, we have estimated quasi-periodic oscillations frequency, and we can see that observational theory closely matches, but there is some discrepancy, like some difference are there. So that might be due to like some more physical processes we need to take into account. So, and I guess that turbulence, because when matter is flowing in, lots of turbulence are there, so it can push the flow outward, and that will take much longer time to fall in. In that case, we can get much lower frequency. So probably turbulence is needed to take into account in this case. So these are the conclusions from this analysis, and what I said, like we did not observe any reflection in this observation. So here we what I discussed earlier. And here I wrote all those equations what we have used to estimate the binary parameters. So we have fitted the light curve using exponential function. From this exponential function, we can get the viscosity time scale, and we related viscosity time scale to the Rosslow radius from where matter is accreting in, and also we can estimate the orbital period. Now the question is, how can we get this binary mass ratio? So there is one or two optical observations, no deep photometry or spectroscopy. These are just observation they made because they could not resolve the optical counterpart properly. So they said that the optical counterpart of this source might be mid or late K-type star. So we have considered mass between 0.5 to 0.8, and this is our orbital period range. This is the lower and upper boundary, and this is the binary parameter of the binary system. So here I left my summary, and thank you very much. Thank you. Any questions?
Audience? Are there any questions in the?
Can you
Yeah.
go back to that Astrosat plot?
Astrosat?
Astrosat plot, right?
Yeah. This one?
No.
The previous one?
Yeah.
Yes.
Yeah, this one. So what are those dashed horizontal lines in you?
Yeah, this is the demarcation line. So it below this one, this 1300. So we did photon count resolved spectral analysis. So we have divided the whole spectrum into two. So one is below this count rate, and other one is above this count rate. So this is actually demarcating this lower flux and upper flux. So, and we have fitted them separately and extracted the flow parameters and tried to get some idea of what can be the reason. So we have seen that flux accretion rate changed almost 10% in a day, and that can be the most plausible reason, because no jet was observed. Earlier literature that said jet can be the origin for this type of behavior, but from our study we did not observe any jet or mass outflow. So it can be due to mass accretion rate. So this is basically demarcating line separating two flip-flop states.
And what is the pin size we use for this activity?
Pin size 5 seconds, I think. Yeah.
Okay, so counts are pretty high.
Yeah. Yeah, counts are high.
Long live India and France friendship.